in this video lecture, just want to say a few words about writing the speed of light in convenient units, especially when we're dealing with things like gamma. So remember, of course, gamma, 1 over the square root of 1 minus v squared over c squared, the Lorentz factor that's involved in time dilation, length contraction, and the like. And we've typically been using speed of light as 300 million meters per second or 300,000 kilometers per second. You can do it in miles per second, 186,282 actually miles per second. And if you want to be a little more precise here, it's actually 299 and some other digits there. But for our purposes, perfectly legitimate to just take 300,000 for kilometers per second or 300 million for meters per second. It's because those numbers are so big and just outside our realm of experience, sometimes it's nice just to think about the fact that it's about 1 foot per nanosecond. In other words, in a billionth of a second, light travels 1 foot, about a third of a meter. So 1 foot per billionth of a second. That's assuming it's essentially in a vacuum. If it's going through a medium, air slightly, but something like water or something like that, that's transparent, it will slow down the speed of light by the so-called index of refraction. But that's a whole other topic for a different course. So 300 million meters per second, 300,000 kilometers per second. Note what happens though if we just deal with v in terms of c. And by the way, we've been using this because I wanted you to get a feel for the magnitude of some of these numbers, or sometimes how small they are too, when we did some of the things, if you've been doing the problem sets, working with some of those numbers. But let's think about this a minute. If we would write v in terms of c, which certainly is useful if it's a high velocity near the speed of light or a substantial fraction of the speed of light. For example, v equals 0.9 c. Look what happens when we calculate gamma then. So we get gamma equals 1 over the square root of 1 minus, well, v is 0.9 c squared, so 0.9 c squared divided by c squared. Well, what's 0.9 c squared? That becomes 1 over the square root of 1 minus, on the top I've got 0.9 squared. So you remember, 9 times 9 is 81. 0.9 times 0.9 is actually 0.81. So we get 0.81 c squared on the top there, the numerator, and a c squared on the bottom. And this is where it becomes nice because, as you probably saw before I even wrote that down, we have c squareds there and they cancel. So this c squared cancels with that c squared. And I'm simply left with 1 minus 0.81. So typically when we do this, we'll just have 1 minus some decimal number, some fraction less than 1 there, and which in this case is 0.19. So you just take the square root of 0.19, 1 divided by that square root, and you've got your answer for gamma, which I think for 0.9c is what? It's about 2.3 if I remember correctly, something around there. Anyway, so makes it very easy for calculations. So often we'll have problems, or you may see problems with v as a certain percentage fraction of the speed of light. But there's another measure that's useful to know about as well that makes our life easier, especially in terms of astronomical distances, and that is the light year, which you may have heard about. So the light year is the distance light travels in 1 year. So it is a distance. It is not a time. Despite the fact about year in there, it's a light year. It's the distance light travels in a year. Distance light would travel in a vacuum. Distance light travels in 1 year. And it's pretty far, right? Off the top of my head, I don't have it memorized. You can actually figure it out if you know 300 million meters per second times the number of seconds in a day is, I think, 86,400. So multiply that out. Then by the number of days in a year, if you take 365 and you get the distance light travels in terms of meters per year, divide by 1,000, you get kilometers if you want. So light year distance light travels in 1 year. And note in terms of c then what the units become. So c then literally is just light years per year. by definition, it's the number of light years it travels in 1 year. That is c. And in these units, then, it's just 1. c travels 1 light year per year, by definition of light years. The distance light travels in 1 year, so it's 1 light year per year. So technically, let me just it's clear. Those are the units for c, then, which equals 1. So we'll put it over here, too, just to be clear. c equals 1 light year per year, and the units in general are light years per year. We'll get rid of this part there. Okay, so c is 1 light year per year, or we could have light month is the distance light travels in 1 month. So we could have c is 1 light month per month. Light day, so c is 1 light day per day. Light second is often used. In fact, 1 light second is the distance light travels in 1 second, which is still pretty far, right? It's going 300 million meters per second. So in 1 second, it's 300 million meters. Okay? So 1 light second is 300 million meters. So, but c is 1 light second per second. If you did 1 light nanosecond per nanosecond, then it's 1 foot. That's the distance light travels in 1 nanosecond, approximately. Okay? The nice thing about this, and physicists love to use units like this, because sometimes they just say we're going to set c equal to 1, because look, it just disappears in here. And the formula for gamma is just square root of 1 over the square root of 1 minus v squared. Now what we're going to do for our purposes is leave c in there, just to remind ourselves it's there, because especially when you're just sort of think about the concepts and try to get your minds around things like this, if you get too sort of simple, it's not really simple in a simplistic sense, but you're simplifying things and saying, just let c equals 1 light year per year. Sometimes you lose track of it. And so it's good to see it in the formula, but then when we actually do problems, if we use light years for a distance, then c is just 1 light year per year, and it works out very nicely that way. So that's just a few notes about convenient units for light, whether we write v in terms of 0.9 c or some fraction of c, and therefore it cancels out, or we use units of light years. And if we say, okay, our distances are going to be in light years, then our time is light years per year, or the velocity is light years per year, and c is just 1 light year per year. So if you use light years, then time is going to be in years. If you use light seconds, then your time is in seconds, and so on and so forth. So long as you're consistent with that, and it's pretty easy to keep track of it, then it makes some of the quantitative analysis and calculations a little bit easier for us.